Today's video will be a little bit different. It'll be a school project for my physics class, and we will be talking about relativity. So for the next 20 minutes, I will be attempting to explain the basics of Einstein's theory of relativity. In order to begin to understand relativity, we must understand reference frames. Reference frames allow us to refer to the position of a physical entity. A common example of reference frames is the use of longitude and latitude on Earth. With these reference frames, we can pinpoint where any entity is on Earth. Another example to help explain this is the frame of reference here on Earth. When we look up at the sky, we see other entities moving across the sky. Thus, they are moving relative to us. In actuality, it is the rotation of the Earth which gives us this illusion. An inertial frame of reference is defined as a frame in which an object obeys Newton's first law, so that it travels at a constant velocity so that no external force acts on it. The only way to achieve an inertial frame of reference would be to travel to deep space, far away from any field of gravity. Only then could you truly find an inertial frame of reference. Unless you are able to achieve this, every measurement you take relating to force will be relative to your environment.
Hey! Somebody get me down! Or up or something!
Additionally, Einstein's equivalence principle in the general theory of relativity relates a free-falling elevator to an inertial frame of reference due to the fact that a person in the elevator wouldn't know they are in free fall, and they would either experience weightlessness or observe that everything in the elevator is moving together or drifting in constant speed. Under such circumstances, no gravitational force can be observed. In its fundamental use, relativity describes the physical properties of one entity with respect to the physical properties of another entity. The easiest way to describe this is by using the analogy of a car traveling. Right now, I am traveling at 30 miles per hour relative to a bystander who is stationary. This is why my speedometer will register 30 miles per hour. However, if another car were to pull up alongside me and also travel at 30 miles per hour, I would be traveling at 0 miles per hour relative to the driver next to me. A video by ScienceTV explains this concept in a bit more depth.
If you are traveling in a car on a smooth, straight stretch of highway, there's no sensation of motion at all.
You mean I could read a book, pour a drink, or flip a coin, and everything looks and feels the same as if the car were sitting still?
That's because relative to the car, you, the book, the drink, and the coin are not moving. Notice that this works only if the car is not changing direction or speed.
So if the car accelerates or turns, pouring that drink becomes a real problem. Well, but constant motion feels just like sitting still.
And if you want to know what it feels like to move at 1,000 miles per hour, just look around. Because of the Earth's spin, we zip along our time zone at a speedy 1,000 miles per hour. And because of its motion around the sun, the Earth carries us through space about 67,000 miles per hour. And because of the motion of our solar system, about the center of our galaxy, we are moving at more than 500,000 miles an hour. But it's not enough to ask, how fast am I moving? We must ask, how fast am I moving relative to some other thing?
But Miller still looks good though, right? Because she's coming up fast. With one complication. The planet is much closer to Gargantua than we thought.
Gargantua. It's what we're calling the black hole. Miller's and Dr. Mann's planets both orbit it.
And Miller's is on the horizon?
Oh, it's a basketball around a hoop. Landing there takes us dangerously close, and a black hole that big has a huge gravitational pull.
Look, I could swing around that neutron star to decelerate.
No, it's not that. It's time. The gravity on that planet will slow our clock compared to Earth's drastically.
Oh, how bad?
Well, every hour we spend on that planet will be 7 years back on Earth. Well, that's relativity, folks.
James Clerk Maxwell devised 4 equations which unified everything known about electricity and magnetism. These equations describe an electromagnetic wave that could travel at the speed of light. This was, in actuality, light. These equations stated that light traveled at 186,000 miles per second, and it appeared that this meant that it traveled at 186,000 miles per second relative to everything. This became a hotly debated topic of relativity around the turn of the 20th century. If Maxwell was correct, that meant that light had an absolute velocity. If the arguments made by classical relativity were correct, that meant that the velocity of the light always depended upon who was measuring it and their motion relative to the source of light. Einstein reasoned that any observer would observe the same physical behavior so long as they were at constant velocity. If the observers were willing to agree to disagree on another aspect of physics, the statement that light had a constant velocity, regardless of relativity, would be true. One element of physics that could be disagreed upon was time. Therein lies time dilation.
Here are 2 starships, one at rest and the other in motion. When the moving ship passes a stationary ship, each fires its laser. Now, according to Einstein, the speed of the laser light doesn't depend on the motion of the ship. So we see both beams traveling side by side at the same speed. The crew of the ship at rest witnessed their laser beam traveling 12 light seconds in 12 seconds, and report that light travels at the speed of 1 light second per second. Correct. But what about the beam from the moving ship? Does it travel only 6 light seconds in 12 seconds? If so, the crew on board the moving vessel would report that light travels at only half speed? No, they wouldn't. But why not? According to Einstein, light always travels at 1 light second per second, regardless of the motion of the person who measures it. How do we fix our picture so that this is right? Part of the answer lies in the fact that the clocks on the moving ship slow down. As we stated earlier, if we must agree on the speed of light, we may have to disagree on the measure of time.
Time dilation is caused by the incorporation of motion into an observed event. Einstein explains this more thoroughly through the observation of light as it travels, since light in the world of physics is considered to be constant relative to any fixed point. So when light such as a laser is emitted from a vehicle, if one vehicle is moving while the other is stationary, an observer recording the speed of light in the stationary vehicle would record the light traveling at a faster rate than that of the person recording the speed of light from the moving vehicle. This is due to the fact that clocks and instruments used to measure time do so by recording events at regular intervals. However, if this measurement is distributed through the acceleration of a vehicle, it will cause the interval to shift slightly to adjust to the force of acceleration that it is interacting with. The phenomenon is easier to understand using 2 mirrors reflecting a beam of light. In a stationary vehicle, the interval between bouncing those lights is constant up and down. However, in a moving vehicle, when the light bounces down or up, it must make a diagonal pathway to follow the interval that it began with. Therein lies time dilation. The beams travel at the same speed, but distance distorts their measured times. In order to accept light as a constant in its velocity, space and distance must be considered as relative to the observer. Thank you for watching this video. I hope you stay safe and have a great day.
Don't say no.